welcome to one of the last sessions here at DrupalCon Vienna. I'm Christopher Gervais. I'm going to be presenting on software update security, trying to introduce it in a relatively easy to grasp manner. So we're going to try to answer these questions. Basically, what is a software supply attack? What are software supply chains? Why are they vulnerable? This bolded part about how we can protect ourselves is where I'm going to get into a little bit more of the technical details using real-world examples to understand the principles at play for how we go about actually solving these problems. And then we'll kind of review what's happening at an industry-wide level within the Drupal ecosystem, and then what you as individuals or people who operate sites can do. So let's start with what a supply chain is. We're all familiar with industrial supply chains, presumably resource extraction, the logistics of transporting and storing those materials, various value-added processes, and there's kind of loops within this until it gets into the hands of the consumer. Software supply chains are a metaphor that maps to that to some extent, but it's basically all of the components and processes and tools that you use to build software yourself. So I've brought in some examples here, but there's so many more things that are not visible to us. But everything from the operating system and cloud environment, and even the firmware that operates the hardware that you're running your systems on, through low-level systems like the GNU utilities, C compiler, etc., the sort of LAMP stack components, as well as JavaScript. Then you get into frameworks with Drupal. This is where you also have packages and all the libraries that you're pulling in from that. And then you have the tools specific to, in our case, the Drupal development, things like DDev, Git is pretty universal, Drush, Composer, etc. So let's just take a quick look at how these are vulnerable. So this is another way of looking at that similar thing. It's the stack, right? The full stack that we talk about. Fact is that every single software application, every single package has bugs in it. We're finding new ones all the time. Doesn't matter how many times you audit it, something's going to come up that in the future, or at the very least we have to assume that that's going to be the case. Now note that I'm pointing out that they're undiscovered and or undisclosed, because the bad guys might know about bugs that we don't yet, right? So this is some of the stuff that we're going to have to try to address. Here's some examples that have made it to the news over the last 10 years or so. This is an accelerating trend. Okay, I'm not going to go into detail about any of these, but at least some of them have probably gotten into your awareness over the years. These are types of supply chain attacks. Okay, so the most obvious one is what we call a malicious code attack, right? Where when you're downloading something, a man in the middle sort of steps in and hands you malicious code instead of the code you're expecting. That's to a large extent what a lot of this ends up looking like. But it could be more subtle. What it could be doing is hacking the composer.json to say that there's some extra piece of software that has to be downloaded that is not actually part of the dependency chain. One of the harder ones to handle are denial of service attacks, where basically instead of handing the package to you, they just stream bits at you, and that can fill up a disk and crash servers and do things of that nature. Version attacks are another somewhat more subtle one. In particular, you'll find things like indefinite freeze, where it will just, the system, so Composer, when it's checking against packages, for example, for updates, if somebody were able to interfere with what's coming down to you in terms of information, it could be reporting that there's no updates needed. This package is the latest version, right? Even though there's now a known bug in it that exposes a security vulnerability. So all it takes is for you not to be able to update your systems for the vulnerabilities to become apparent. And then there's this emerging threat now with all of the utilization of AI, where AI will hallucinate the existence of a package that doesn't exist. And these are actually kind of predictable in certain ways. And so somebody could go and essentially squat that package. They build a package and publish it under that that name, and then they can inject whatever they want into your code base if you're not careful about that. So these are things, these are the types of things that we're trying to protect against. The slop squatting one, I don't think we have an actual solution for yet, but it'll come. So let's look at how we protect ourselves. So this is the part where I'm going to start getting into some of the actual techniques and technologies that we use to address these kind of problems. I'm going to use real-world examples throughout each of these to kind of illustrate the underlying dynamic at play. And then as we go towards the end, we'll be able to pull that together and see how that fits into when you run Composer, what happens. So the first thing is validating signatures and documents. So everybody presumably has a checking account. And when you start a checking account, this might no longer be the case considering how you can start checking accounts online without ever having to go in and visit a branch. But at least for old folks like me, you used to have to go in and sign a signature card like that. And the reason for that was that when you wrote a check, handed it to somebody, they deposited it at their bank. That bank would send the physical check. Way back in the day, they would send the physical check to your bank, who would then compare your signature on the check to your signature on the reference card that they had to validate that the signature is correct, that it was your signature and not somebody who had stolen your checkbook, right? So what the bank is doing in this case, the technical term is they're verifying the authenticity of your signature, okay? That's going to come back. That terminology is going to come back. So I'm going to use the terminology we use from a technical standpoint as we look at these different examples. So another example of a type of signature is on contracts. So often on contracts we'll have one or two signatures from the parties that are actually being bound by the contract. But we have another type of contract or signature on contracts, which is a witness signature. The witness in this case is not bound by the contract. All they're doing is saying, I watched the person sign the contract, and I made sure that it is their signature on that contract. And so if one of the parties were to repudiate, were to say, that's not my signature, it's a forgery, the witness can be called in to say, no, I was there, and I can attest to the authenticity of that signature, right? So they would be asserting the authenticity of the signature in that case. This goes a little further. Some contracts are really, really important and need to be notarized, right? When you're purchasing a house, for example, I know in Canada, you need to have a notary present because it's a large sum of money that's going to be transacted. Mm-hmm. Part of what they're doing in this contract is they're making sure that you actually understand the terms of the contract, that you're not just clicking through an agreement, right? They're also making sure that you consent to the contract, that nobody's holding a gun to your head or anything of that nature, threatening you into making that contract. But the part that we're more interested in is how they would have certified copies. Two or more parties might need a copy on record of the contract. And so we need to make sure that those copies of the contracts are all going to be the same, because you don't want to go to court and have two versions of a contract that disagree over some important point. And so that's the role that a notary plays in this case. So they'll put their seal on the contract, that nobody else has access to their seal, and then separately they will record the fact that they sealed that contract, they witnessed the signature, they ensured that the comprehension was there, etc., in a logbook. They keep track of this, right? And that's what a notary does and why we pay them for their services. So in this case, the notary is validating the authenticity and the integrity of the contract, right? That contract has not been changed because their seal is on every page of that contract, or at very least on the signature page. So now we're going to get into a little bit more of the technical part. So the main thing about public key cryptography is what's referred to as asymmetry. Okay, so a real-world example of this is if you want to send me a letter, all you need is my address. That's a piece of public information, right? It'll be posted online, in a phone book, wherever you might find it. For me to access that letter you sent me, for me to get access to it, I need a private piece of information. I need my key that nobody else has access to open the mailbox and get the letter that you sent me. So this idea of public and private are important and are going to come back as we go. But the most important element of this in terms of asymmetry is that it doesn't work in reverse. My having a key to my mailbox doesn't help me send you a letter, right? At all. So that's one of the really important elements of this that we're going to, again, it'll come back in a moment. So when we talk about keys in public key cryptography sense, what we mean is these files that contain long strings of characters. They look random to us, they're not, and they have some special properties. But essentially we use very complex math that I do not pretend to understand in any way, shape, or form. I just trust the PhDs on that front. And they use very large random numbers to generate these two files, these keys, that have a relationship between each other that we're going to look at in a moment. And then by convention, we call one of those keys private, and we try to keep it as secret as possible, and then the other one public, and it acts kind of like an address for us, and we can share it. So, as I mentioned, the private key has to be kept secret. It has to be private to you because it's the thing that grants you access to the mailbox in this metaphor, right? The public key is the equivalent of your address and something that you want to share broadly. The asymmetry in this case is if I encrypt a message, that's what these keys are used for, things like encryption. If I encrypt a message with it, I can't use the same key to decrypt that message. I need to use the other key in that key pair to decrypt it. But it goes both ways. So this asymmetry has to do with whether you're sending something to me that you want to have secret, or, as we'll see in a moment, something that you want to make sure came from me. So in the sort of standard model of how this was built out, spycraft and stuff, they wanted to send secret messages to each other. They would use a public key that was known to be one of the two keys in a key pair that the person they're sending their message to, they have access to that public key. They can use that to encrypt a message and know that the only people who would be able to open it would be people that have that private key. In this case, one person ideally, right? Now in this case, the whole point of this is for the message to be secret. In our case, in terms of software security, we don't really care about that part. We care about this other aspect of this, which is sort of the inverse of encryption. So in this case, what we're going to do is we're going to sign the message. So what we're doing here, I'm just going to flip this back and forth. And pay attention to the public and private keys. They basically just flip places. Okay, so in this case, instead of encrypting, I want to send a message that the recipient will know came from me. And the way that I do that is I encrypt it with my private key. Now, anybody who has access to my public key can decrypt that message. And so if I send the unencrypted message and the encrypted message to somebody, they can use my public key to decrypt the encrypted version, and it should match exactly the plain text version. And that way they'll know that this message is coming from me because nobody else has access to my private key. Okay? So again, in this case, the message is not private, right? That's not the point of this type of communication or encryption. Now, how this works in real life with, say, encrypting your messages in email is that you just do both, right? You can say that I'm signing this to make sure it's coming from me, and then I'm encrypting it so that with the recipient's key and so forth. So you can layer these things. That's not especially relevant to this, so I'm just pointing that out. The last piece of functionality we need to understand is hash functions. Now, the problem with this model is that the ciphertext, the encrypted text, is roughly the same size as the original text. So in order for me to send a message that you know comes from me, I need to double the amount of bandwidth used to send it to you. Instead, we can use hash functions to sort of take a shortcut. A hash function would be comparable to like a fingerprint, in a sense. It's a fingerprint of a file. And it's a one-way program, and essentially what it does is it just scrambles the content and then reduces it down to a fixed length code, what we call a hash sum, which is usually just hexadecimal. And the thing is that you can't go in reverse. So with this hash, you can't figure out what the original message was. All you can do is make sure that the message is the same thing as it was before. So that's where this interesting usage component comes in. If I feed the same input into one of these hash functions, it's always going to end up coming out with the same hash sum. So if I'm sending a message to somebody and they want to make sure that that hasn't been corrupted in any way, like say you're downloading an ISO for an operating system, it's a whole lot of data. When you download it, 750 megs or more than that now, several gigs for a DVD ISO, and you would end up having to ensure that every single bit is correct on that, or you could get a corrupted install. So we use hash sums to be able to compare that. I have the data that I want to make sure is correct. I pass it through the correct hash sum. It comes out with or hash function comes out with a hash sum. I compare it to the place I downloaded it. Those match. I know that the copy I have is legitimate. So now we're starting to get much closer to what we're trying to do when we're downloading packages off of Packagist or Drupal.org and making sure that they haven't been hacked along the way. So let's take a look at how this works. So without any extra security, package updates work roughly like this. So when a module maintainer or a theme maintainer puts a new tag down in their Git repo and creates a release node on Drupal.org, that triggers the packaging pipeline, which is like a CI process essentially. And that generates a zip file of the code in the Git repository for that module. They then generate a package metadata for Composer. So this is the part that allows Composer and packages to talk to each other and make sure it understands what version is there and what the dependencies are and what versions specifically are dependent upon by this package and so forth. So it generates all that metadata. When you come along and with Composer want to update your local code base, you're going to, or Composer rather, is going to download that metadata, figure out which version of all the different packages are required, and then it's going to go and download the zip files that were generated by the packaging pipeline onto your local environment or into your server environment or your CI environment, etc. The risk, as we looked at earlier, would be that that file has somehow been corrupted, okay? That some nefarious person has replaced it with something that's going to gather your bank data or something like that. So this is how package verification works. We now have all the tools and an understanding of how this all fits together. Everything that happens in this one still happens, but in addition, the packaging pipeline uploads the zip file and the package metadata, so also the piece that Composer looks at, up to a TUF server. Okay? So TUF stands for the Update Framework. We'll look at it a little bit later. And that server generates some additional metadata, including a hash sum for the zip file, and then it uses its private keys to sign that hash. That's what happens in the publishing pipeline. The Composer component, there's a new plugin for TUF for Composer, will do all the things it normally does, but every time it downloads a file, so when it downloads the package metadata, when it downloads the zip file, it's going to check in the TUF server metadata that's also published, and it's going to look up what the hash of that file ought to look like. And then it can take a hash of the file and compare and make sure those are correct. And the way that it knows that that hash is valid is by looking in the public key that ships with the Composer TUF plugin and decrypting the signature of that hash that was generated by the TUF server and inserted into the TUF metadata. So I know that part probably doesn't make sense. It took me like a year of actually building some of these things before it started to really make sense, but I'm not going to go into sufficient detail to kind of prove anything to you about this, but this is the general way that this operates. And if you're really curious, feel free to track me down. I'm going to be here all day tomorrow as well, and I can talk to you all day about this stuff. So let's take a step back now that we've looked at sort of what the process looks like and see what's happening at an industry-wide level. So these are just some of the examples of both governments and industry and academia collaborating in various ways to come up with the kinds of techniques that we just saw to help secure package security at sort of a global level, right? Coming up with systems like TUF, so the update framework, which defines how you can generate metadata that you can verify in a way that can prove to you that those hash zones are correct and trustworthy, and then use those to validate that the packages that you've downloaded haven't been hacked. So there's additional things that are we haven't started to work on in the Drupal sphere yet, such as in-toto and SBOMs. SBOMs is a software bill of materials, so that basically lists all of the other packages that come along with yours as dependencies and which versions and things of that nature. In-toto looks at trying to essentially generate logs of the entire process that can be audited along the way, so that when you're comparing all of this metadata at the end of the day, part of what you're comparing is knowing who did what when. Was it built on GitLab? At what time? Which VM was used? Things of that nature, to be able to identify where there might have been a breach if one were discovered, giving audit trails and things of that nature. These two things at the bottom are both agencies. One is of the German government, I believe. Another is a consortium, I think, if I recall correctly, of companies that are interested in ensuring that open source software that they all depend on are able to be kept secure, and they've been funding a lot of this kind of work along the way. So the update framework is one of these sort of specifications, a standard that's come out. It came out of academia, where they looked at and analyzed all those attack vectors that we looked at earlier, and came up with the principles with which we can use to do this, to build a system that can be trustworthy. The main thing it's looking at is compromise resilience, so making it so that if somebody were to hack something, that you can find a way back out of that safely. And then integrity and freshness, make sure that you're getting the most up-to-date ones as we go. I realize we're running out of time. Let me just quickly look at the automatic updates initiative within Drupal, is sort of how Drupal is implementing a lot of this. The rugged server is the piece that I've been building over the last couple of years to make sure that we can generate the metadata securely. There's also the PHP Tough library and the Composer plugin. So the Composer plugin uses the Tough library to be able to do that client-side verification that we looked at. And then the automatic updates system is sort of in beta on the back end, and there's various challenges with getting some of the package manager components into core, but that's an ongoing effort. There's a couple of Slack channels where we talk about some of that stuff. And then in terms of what you can do to protect yourself, only use software that really takes security seriously. Drupal does, and it's proven it over and over again. I'm also talking with Nils at Packagist about potentially implementing something like this for them down the road. You need to make sure to keep your sites updated. This auto updates initiative is the kind of thing that will make it much easier for smaller organizations to do that don't have engineers on staff that can do all of the DevOps setup. Auto updates is a really good solution for that kind of thing. And if you want to try to do something personally on this basis, you can help test it. There's an issue where we have some of these tests. You want to report any security issues responsibly, support the Drupal Association and developers who are maintaining this code so that we have the opportunity to fix bugs as we come across them. If you're a developer, make a point of writing secure code, and then just stay informed. And all of you, of course, being here are already doing that. So thank you very much. I don't know if we have time for questions, but feel free until I'm kicked out. No? Okay. Well, thanks again.
One question.
Oh, go ahead.
So if you just go back a couple slides to...
What about a mic?
Oh, yeah. Maybe.
I'll repeat your question.
Yeah, okay. If you just sort of, somewhere around here, talking about how maybe back further. So we know that to the sort of encryption, this, yeah, right here. So,
okay.
So by definition, if you just go back one slide, here is what Composer is doing today without any of the extra stuff we just talked about.
That's
and
right.
if you go forward one slide, now Composer's doing a bunch of other stuff. What's being done to ensure that this is every package every download, right? Something has to be, doesn't this have an implication for composer's performance?
Yeah.
Ah, yes. That's a good point.
Big yes.
I know the
It's-
answer to this question.
It is,
I'm asking
okay.
so that I can
So
make
the
it-
question is, with Composer now having to check all of this tough metadata as it downloads things and check the hash against things and so forth, is there a performance implication to this? Yes, there is. It's much, much worse on Mac than on Linux. Okay. I'm just going to say it's about 6 times worse on Mac, based on my experience today. I'll work on it. It's not I didn't write that piece, but whatever. But it's about twice the time on Linux. So it has to download a bunch of other stuff, do a bunch of verifications along the way. There's a cost to security. In this case, it's a little bit of extra time whenever you do a Composer update.
But it's,
Spend a lot of money optimizing it.
but you're
We'll work
tracking
on it.
this.
So unfortunately, we got the next session
Yeah.
coming in here. We're gonna have to cut off questions.
Okay.
So